All right, this is Unit 4, Lesson 10 in Algebra 2, and we're talking about projectile motion. Now, projectile is something that is like moving through the air. So we're going to talk about how quadratics apply to anything that is going to go up and then come back down, because that's what gravity does to objects. It makes it come down. And I think this is a really cool lesson. And I know that they're kind of like word problems, but I hope you'll find it interesting too, because this, of anything we do in math, really does have a lot of real life applications. So on problem 1 here, it says a soccer ball is kicked from the ground with an initial upward velocity of 90 feet per second. The equation h of t equals negative 16t squared plus 90t gives the height h of the ball after t seconds. Okay, and the thing to remember here is velocity is the same thing as speed. Now what's happening here is we, again, kicked a soccer ball from the ground. It went up in the air and it's going to come back down and hit the ground. And when that happens in math, okay, it's almost like we have a coordinate system here. And we're mainly going to deal in quadrant 1. Okay, that's where real life things tend to happen. And what we do is we label the x-axis as t, standing for time. Okay, oops, so time. The t-axis instead of the x-axis. And the y-axis is going to be the h-axis, standing for, oh, it's erasing things here, standing for height. All right, so instead of y, we have h. Instead of x, we have t. So we're saying that the ball is going to be kicked from the ground. So we could say like, hey, it starts here at the ground. It's going to be kicked up in the air, and then it's going to come back down. Now, and then it will land. This is parabolic in shape. Notice it made a parabola. Okay, it's like a sad parabola, but it's still a parabola. Anything that goes up in the air and comes back down is going to make this shape. Okay, it could be skinnier, it could be fatter, could be flat, wide, whatever, but it's going to be parabolic in shape. So let's look at our first part of our question. It's broken down to 3 parts. It says, how many seconds will it take the ball to reach its maximum height? Okay, so let's break this down. Where is something at its maximum height? We know this, we really, really do. Maximum height is at the vertex. Okay, so, right, so we could agree, like on my little diagram here, that blue dot right here would represent our maximum height. But the question here is not what is the maximum height, it is how long or how many seconds will it take to reach that. Well, seconds is time. So we want to know, okay, what's the t value here? Okay, because I didn't label any of this. What is the value of t when this ball is at its maximum height? So basically what we're looking for, I'm going to say t comma h here. We're looking for the time, or the x value of our vertex. Okay, even though I'm using t and h here, it's still like x and y because it's the first value. Now, how do we find the x value, or in this case the t value of our vertex? There's a formula. We mainly relied on our graphing calculators a lot, but there was a formula that told us the x value of the vertex, and that was x is equal to negative b over 2a. And right now we are just replacing t with from the x in the equation here. So it's t is equal to negative b over 2a. Now where am I going to apply this formula? We're going to apply it to the formula that it gave us. It gave us the formula that represented, or the equation, let me say, that represented the pathway of our ball. So let's label our a and our b here. A is going to be the number in front of t squared. Just like a is the number in front of x squared, a will be the number in front of t squared. So a is negative 16. B is going to be the number in front of t, which is positive 90. So now we are just going to plug these in for a and b in this little formula that I circled right here in green, and we will compute time. So time that the ball is at its maximum height will be negative and then 90 over 2 times a, which is negative 16. So we have negative 90 divided by negative 32, and that's going to equal about, let's see, 2.8125 seconds. So we're going to write that on 1a here. So 2.8125 seconds. That's how long it took the ball to get to that highest point. Pretty cool. Now let's look at B. It says, what is the maximum height of the ball? So we know this is the time the ball was at its highest point, but what was that highest point? And so we're wanting to know, what is that H measurement here? So basically we're solving for Y. So let's think about it. If we know the time the ball is at its highest point, which was, again, 2.8125, we could plug that in for the T's, and that will give us the value for H at that given point in time. So that's all we're going to do here. When we say H of T, again, that represents H at a given time. We're plugging in 2.8125 in for our T's, and we're going to calculate. So we have negative T from the formula again, right here, times 2.8125 squared plus 90 times 2.8125. And all of this, okay, right here, just gets typed into your calculator with parentheses and everything, and you just hit equals. And that's going to equal 126.5625, and it is our height, which is in feet. So let's write that down. So because we knew the time the ball was at its highest point, we could plug that in to find the highest point. Pretty amazing. So 126.5625 feet. Okay, give the domain and range of this function. Okay, so domain, remember, means x's, which here we are going to say t's. And range usually means our y's. In this situation, it means h's. So your domain and range, you're asking for like what was the starting or your lowest value for that given variable to your highest value. So when it comes to the domain, we're talking about time here. What was our starting time that the ball left the ground, and what was our ending time when the ball hit the ground, which would be represented here. So what is the time? Our starting time would be at 0 seconds. But what is the time when it hit the ground? We don't know that yet. So that's the first thing we have to do, is to find the whole domain. We need the starting time and the ending time of what that ball did. So how can we find that? Well, we're going to start with this equation, negative 16t squared plus 90t. And this is equal to our h of t, which is height at a given time. Well, at a given height at a given time, well, we don't know the time, but we know when the ball lands right here, the height will be 0 because we are going to be on the ground. We are 0 above the ground. So if we set this equation equal to 0 and then solve for time, we will solve that missing piece of what time the ball hit the ground. So negative 16t squared plus 90t equals 0, a height of 0, remember? And we only have one variable here. We have variable of t that we are solving for. So how can we solve for t when t is squared? It's like solving any other quadratic we've done. We can try factoring. Now, we can't do 1, 2, 3 factor tree because there's only 2 terms. So I would think here, what do they have in common? Okay, they both have t's, but what is the largest number that goes into negative 16 and positive 90? And that's going to be negative 2. And we can take out 1t. So now I'm dividing negative 2t out of both of these terms. So negative 16 divided by negative 2. And again, I made my GCF negative because I do not want a negative as in my first term. So I get positive 8, and then we take away 1t, so we have 8t. Then we have positive 90 divided by negative 2 is going to be negative 45, and t take away t, okay, those are gone. We always have to wrap that part up and put the GCF on the outside. And this is all set equal to 0, representing a height of 0. Now to finish solving for t, when we factor, we t-bar, and each factor gets set equal to 0. So negative 2t equals 0, and 8t minus 45 equals 0. Then each side gets solved for 0. So on the left, we would divide by negative 2, and we get t equals 0, which does make sense because we know that the ball started at a time of 0 on the ground. That's when all of this started. My second one will add 45 to both sides. So we have 8t equals 45, and then divide by 8, and 45 divided by 8. Okay, we will deal with decimals here because we're dealing with time, and that would just make a little bit more sense. 5.625 seconds. Okay, that number right here, 5.625, that's what time the ball landed on the ground. So what is our domain here? Our domain, we start at 0, and I'm writing it down here on C, and we're saying that's our starting point. So we always have X in the middle of all this, and our signs are always just going to do this right here. We're saying 0 is less than or equal to X, which is less than or equal to our ending time, which is 5.625. All right, so that was how we found our domain. We needed the starting time and the landing time. Now, the range, again, range is your y's. So since y is height, we want our lowest height of the ball, which is going to be 0. It started on the ground, and we want our highest point of the ball, which is going to be when it was up here. And we actually already found the highest point of the ball, right? It was that H, that was part B. We found the maximum height, which was, let's see, 126.5625. So that's what we're going to put here. That our lowest point was 0, and we're going to say it's less than or equal to. Now we're going to say y, or if we used h, that would be fine too, which is less than or equal to 126.5625, which was our highest point. All right, we're going to keep kind of doing these same types of problems in different ways. We can use factoring to solve a lot of times, and we can also use quadratic formula. All right, it's going to be great. All right, on number 2, it says an apple is launched directly upward at 64 feet per second from a platform 80 feet high. The equation for this apple's height, h, after time t seconds after launch is h of t equals negative 16t squared plus 64t plus 80. And then our question, what is the height of the apple after 3 seconds? All right, so I'm really bad at diagrams, but basically we've got this platform. That's as good as it gets. And we got some kind of apple shooter, I guess, and we're going to take this apple, let's do red for apple. And on this platform, somehow we are launching this, kind of like maybe Angry Bird style, into the air, and then it's going to come back down and hit the ground. Okay, so we are already starting 80 feet above the ground, and actually for this one doesn't really matter, but that's kind of what's going on here. So remember that where we start, okay, that's our h-axis, and our x-axis is now our time. So we're wanting to know, okay, this would be 0, 1, 2, 3. What is the height of the apple after 3 seconds? So what we're saying here is t equals 3. Well, we're asking what is h when t is 3. So this one's actually really simple. We don't need to overcomplicate it. If time is 3, we have t's in the equation, okay, right? There's 2 t's. If we plug in t, or 3 for t, and then solve this equation, we will have the height at that given point. And that will be it. So what we're finding here, okay, is h of 3. What is that? And we're using this equation here. So negative 16, and then we had t squared, so we're going to put 3 in the parentheses for t and square it, plus 64, and then we had a t, so we're going to plug in 3 for that 3 seconds, plus 80. And again, all of this right here just gets typed into your calculator, just like that. And we get, okay, h of 3, meaning our height at 3 seconds is equal to 128, and we're going to say 128 feet. And that one's done. Okay, sometimes these are not really, really complicated. Okay, so if we want to find height at a given time, plug in that time value in for your t's and solve. Okay, on number 3, we have a toy rocket is launched vertically upward from a 12-foot platform with an initial velocity of 128 feet per second. So we're starting, again, 12 feet above the ground for some reason, and it's launched in the air, and then it's going to come back down and hit. Okay, so this is 12. And again, I'm not great at diagrams, and I don't even care. It's fine. The height h after time t seconds after launch is given by the equation h of t is equal to negative 16t squared plus 128t plus 12. How long will it take the rocket to reach the ground? So that's our question right here. Always go to the last sentence to know what it is that it's wanting you to find. How long will it take the rocket to reach the ground? So we're finding height, which is using this whole equation. Okay, and when we are on the ground, what is the height when we are on the ground? Okay, the height is 0. So we're wanting to know, how long did it take for the ball to, or the rocket to get on the ground, a height of 0. So what we're going to do, because height equals 0, we are going to replace h of t with 0. That is equaling a height of 0. We're setting the equation, negative 16t squared plus 128t plus 12, set equal to 0 because that represents, okay, height equals 0 on the ground. Now, we have a quadratic that is set equal to 0. We've been preparing basically the whole past few weeks for this situation. Let's use a quadratic formula. If we want to solve for t, which is squared, that's the same thing as solving for x squared, we could use the quadratic formula, which is negative b plus or minus square root of b squared minus 4ac all over 2a. And instead of saying x is equal to all of this, we can say t, or time, is equal to all of that. We're going to say that a is the number in front of t squared, which is negative 16. B is equal to 128. C is equal to 12. And then why could I label all of these? Because our equation was set equal to 0, and the rule for solving quadratics was that our quadratic just had to be set equal to 0. So this all works. So plugging it into the formula here, we're going to say time is equal to negative, and then our b value, 128, plus or minus big square root. We have 128 squared minus 4 times negative 16 times 12, all being divided by 2 times negative 16. So remember our rule. Use your Casio or even your graphing calculator, because we don't need simplified radical answers here. Start by making it a fraction first and type it all in using your plus sign first. Okay, when you type all of this in, using the plus sign, the first answer you're going to get is negative, let's see, I did it, negative, where's my pen? Negative 0.0927. And it keeps going on. And then our second answer, okay, that was our adding answer. My second answer for t, when I subtract, is going to be 8.0927, on and on. Well, let's think about this real quick. Can we have negative time? No, we can't. So just like with our previous lesson where we don't have negative measurements of length or width, we do not have negative measurements of time. So we get to cross off our negative answer. Again, why is it negative? It's because if we continue this backwards from where we started on our 12 feet above the ground, we would get to that negative time point. Okay, right? Anyways, it's moving backwards, which we really can't do, but that's why it's doing it mathematically. So our time that we like, we're going to say the time that it took for the ball to hit the ground is 8.093. Let's go to 3 decimal places, seconds. Super fun. On number 4, it says a penny is dropped off the Empire State Building, which is 1,250 feet tall. If the penny's pathway can be modeled by the equation h of t equals negative 16t squared plus 1250, how long would it take the penny to strike a 6-foot tall person? All right, every time I have a problem like this in math the last few years, someone always says, that's going to kill the guy it hits. We looked it up on Mythbusters. It doesn't actually kill them. It probably hurts, but it's not going to kill whoever this lands on, so don't worry. So basically, we've got the Empire State Building really, really big. Okay, it's how big? 1,250 is where we're going from. And we're going to have someone up here, and they're going to, this is obviously not to scale, they're going to drop their penny, and it's going to come down, and it's going to hit this guy who is 6 feet tall. So we want to know, how long does it take to hit this guy? Well, that's our question. So we have an equation. We have negative 16t squared plus 1250, and we're setting it equal to the height of what? Usually we set equal to 0, but this time we're saying it's going to hit a man who is 6 feet tall. So we're saying our height is 6. So instead of setting this equation equal to 0 right now, we're setting it equal to 6. It's not hitting the ground. It's hitting a man who is 6 feet tall. So We have negative 16t squared plus 1250 equals 6, and we are being asked to find how long, which is time, so we are solving for t. Now again, lots of different solving methods here, but because we have a t squared and not a regular t, we are missing the b value, which means that we can use our square roots method, which means isolate t squared, get it by itself. So let's minus 1250 from both sides. We have negative 16t squared is equal to 6 minus 1250, which will be negative 1,244. We are not done isolating t squared yet, so we're going to divide by negative 16 to both sides. What we do to one side, we do to the other. So t squared is equal to negative 1244 divided by negative 16 is positive 77.75. And I know I've told you in the past, don't take square roots of decimals, but I guess apparently the only time we can is when we're dealing with real life situations, which again, most of the time in math, we're just dealing with regular equations. So here, decimals are fine. To solve for t squared, to t, we're taking the square root of both sides. So we get t is equal to, and we're going to say plus or minus 8.818. Okay, now we always say plus or minus to begin with. That means positive 8.81 seconds and negative, but we only want positive time. So we're going to say the positive 8.818 seconds is the answer that we are looking for here. That's how long it would take the penny to start at the top of this building and to hit a man who is 6 feet tall. On number 5, we have some fireworks are fired vertically into the air from the ground at an initial speed of 80 feet per second. The equation for this object's height, h at time t seconds after launch, is h of t is equal to negative 16t squared plus 80t. Find the domain of this function. All right, so we have the ground here, some fireworks were shot in the air, and they're going to land back on the ground. When they were at their highest point, I'm sure that they looked, we had some fireworks, right? Let's make them pretty. And we want to know the domain. So again, changing colors here. Domain means our x's, okay, or our t's in this situation. They started here, they went up in the air, and then they landed on the ground somewhere. So we're wanting to know starting and stopping time. Okay, where did it start for time and where did it stop? Beginning and ending. Now again, however you want to think of it, but that's what our domain is asking. But for which variable? For t, because domain is x's or t's in this situation. So what we're going to do is we're going to take the equation, negative 16t squared plus 80t, and starting and stopping, well, we're always setting it equal to a given height, again, because it's set equal to h of t, which is height. And starting and stopping on the ground. So we're going to set this equation equal to 0 because 0 represents being like no up or down, just on the ground. So we're setting the equation equal to 0 and we're solving for time. Because we are given the t squared and the t, I can see that they have something in common. We can factor by taking out a GCF. So what's the largest number that they have in common? Well, actually 16 does go into 80. And we're going to make it negative because we never like our leading term to be negative. And they both have t's, 2 t's and 1 t. I can take out 1. So this is a GCF type of factoring here. So negative 16t squared taking out negative 16t is just 1 positive t left. Positive 80t divided by negative 60t is negative 5. We always put that part in parentheses and put the GCF on the outside. And again, all of this is set equal to 0 to represent a height of 0 when it started and stopped. Okay, it started and stopped at a height of 0. And then we always t-bar, separate the two factors, and each factor gets set equal to 0. And we solve each of these for t. All of this should look very familiar to everything we've been doing. We would divide by negative 16. So we have t equals 0, and that really makes sense because that's where we started, right? Our starting time is usually 0 when we're doing things on purpose here. And we would add 5, and our second time of 5 is when it hit the ground. Okay, those 2 times. we have our starting time and our stopping time of how long basically our firecracker stuff was in the air. So what is the domain? Our domain, okay, again, we're going to say X, or I don't care if we use a T, and we're going to put these two signs on either side always. It's just how it works. Our lowest is on the left, and our highest is on the right, and that would be our domain right there. Starting time, stopping time. On number 6, it says the Apollo's Chariot roller coaster at Busch Gardens moves at 101 feet per second. Oh, that's fast. The equation of the ride can be represented by the equation h of t is equal to negative 16t squared plus 101t plus 10. What is the maximum height reached by this ride? Okay, so we want to know its highest point. So when we find max height, we have to first, it's like a two-step problem. First, we have to find time of max height. And then second, we plug that in to the original equation. Okay, that's what we're doing when we find the maximum height. Two steps. First, we have to know what time. It didn't tell us the time it was at its highest point. So if you remember back to problem 1, we did this. We're going to use the formula to find the time of the highest point. Again, the maximum height, so it's going in the air and it's coming back down. Remember, that's going to be at the vertex when it's at its highest point. So that would be found by doing negative b over 2a to get the time of the highest point. This is for our step 1. So our a value here is negative 16 and our b value is 101. C is 10. So to find the time we're at our highest point, we're saying negative and then our b value of 101 over 2 times a, which is negative 16. So what is the time of this maximum height? That's going to be about, let's see, 3.15625. And I don't think I want all those, so let's say 3.156 will be good enough for right now. All right, so we're going to plug that in. Now we know the time that it was at its highest point. Now we can plug this number in for the t's in the original function and get an answer for h. So again, we're finding h of 3.156. And we're plugging this in. This represents our t's. So we have negative 16 times 3.156 squared plus 101 times 3.156 plus 10. And we're typing all of this into our calculator. Okay, and when we get out of there, we're going to get out that our height, technical difficulties. Okay, our height is going to be about 169.39 feet. That is our highest point. So again, to find maximum height, first we need the time it's at its maximum height, and then we have to plug that back into the original equation and solve for h. All right, number 7, Eva is jumping on a trampoline. Her height at a time t can be modeled by the equation h of t equals negative 16t squared plus 20t plus 6. Now this question's a little bit different. It says, would Eva ever reach a height of 14 feet? So will she have a maximum height of 14 feet? Remember, maximum height is at our vertex. So basically we're wondering, what would her technical vertex be here? And is that y value, that h value, is it at least 14 feet high? If it is, then yes, she could reach a height of 14. If no, it's lower than 14, then no, she cannot have a maximum height of 14. So again, to find maximum height, which is what we're essentially asking it, we have to first find the time of the maximum height. Okay, so 2 steps. Okay, our first step, we want to do t is equal to negative b over 2a, because that gives us the time of the highest point. A is negative 16 and b is 20. So let's plug those in. So to find the time of the maximum height, we have negative and then our b value 20 over 2 times negative a, which is negative 16. So this would give us, let's see, about 0.625. So that's the time of Eva's maximum height. Now we're going to do our step 2, which is plug in for t. We're finding h of 0.625. And we're calculating this. So we have negative 16 times 0.625 squared, using again this equation above, plus 20 times 0.625 plus 6. And we just go now and type all this into our calculator, and we're going to get 12.25. This is Eva's highest that she can go. So going back to this question up here, would Eva ever reach a height of 14 feet? The answer is going to be no, because the highest she can go is 12.25 feet. All right, number 8. A diver is standing on a platform 25 feet above the pool. He jumps from the platform at an initial velocity of 10 feet per second. Okay, so we know that his velocity is 10 feet per second. His starting point was 25 feet above the pool. So it says we're using the formula h of t equals negative 16t squared plus vt plus s, where h is the height above the water at time t seconds. V is the starting upward velocity, and s is his starting point. Write an equation to model the dive. So this is really just trying to sound all complicated, but it's really not. Okay, we're finishing the equation here. We need to plug in a number for v and a number for s, and it's telling us that v represents the velocity, which we were given above. Velocity is 10 feet per second. S is his starting point, and we know he started 25 feet above the pool. So it's helping us make this connection that whenever it was telling us in all these problems before what the speed was, that was the velocity, which was the number that was in front of the t. When it was telling us the starting height, that was our constant. And all of these equations, if you went back and looked at them, that would be the pattern here. So the equation we're using is negative 16t squared, that was given right here, plus vt, well, our velocity was 10 feet per second, so we're going to say 10t, plus s, which is our starting height, which is 25. And that's it. That's all I wanted to know. Again, making that connection that this number in front of t represents speed, the constant represents the starting height. So let's look at part B. Find the diver's height after 2 seconds. So it's so much easier when they give us time, okay? They're telling us find the height. What is the height equal to at t seconds? Well, we just plug in 2 for these t's and we calculate. So we're finding h of 2. We have negative 16 times 2 squared. Again, that 2 is for 2 seconds. Plus 10 times 2 plus 25. And we type all of this into our calculators and we get negative 19. Now, why can we have negative 19 feet on this one? Because remember, he was going underneath the water when he dove. So the height of where the water is, let's see, he had this diving board and here's the water. The diving board was 25 feet above ground level, okay, from the water. Oh, I did not want to do that. It keeps switching to erase around me. And then he's diving, this dude right here, he dives and he goes underneath the water. So we're at negative 19 feet here. That's what's happening. Don't laugh at my diagrams. Okay, the last one for this lesson. We have an astronaut on the moon throws a baseball upward with an initial velocity of 10 meters per second, letting go of the baseball 2 meters above the ground. The equation of the baseball's pathway can be modeled by h of t equals negative 0.8 t squared plus 10t plus 2. Now, the same experiment can be done on Earth, in which the pathway is modeled by the equation h of t equals negative 4.9 t squared plus 10t plus 2. Now, notice our equations are very similar. What's different here is basically the gravitational pull, right, between the moon and the Earth. So our ending question is, how much longer would the ball stay in the air on the moon compared to the Earth? So we have a stronger gravitational pull on Earth. So it's going to hit the ground sooner on Earth than it would on the moon. And the question is, how much longer? So it's asking us about time. Now, when we're asked to solve for time, okay, then we are going to end up solving for t, and t is squared, so we're going to be solving the quadratic. And in this case, I would use a quadratic formula because we're already dealing with an a value that's a decimal. how much longer would the ball stay on the ground? So for each equation, we're going to set this up in two different ways. So we're going to have to find out how long the ball stayed in the air on the moon versus how long the ball stayed in the air on Earth. So we're going to say here time on the moon, and then over on the left, or yeah, on the right, I can do left and right. Okay, we're going to say time it takes to hit on Earth. So we have two different problems. The equation for on the moon, we had negative 0.8 t squared plus 10t plus 2. And again, we're going to set this equal to 0 because we want to know how long it takes the ball to hit the ground. If it's staying in the air, it's in the air until it hits the ground. Then hitting the ground would be a height of 0, which is why we're setting it equal to 0. So we're going to think about this. Our A value is negative 0.8, our B value is 10, and our C value is 2. Because I'm solving for t, I'm going to plug all this into the quadratic formula so I can get my two answers for t. So we have negative and then 10 plus or minus big square root. We have 10 squared minus 4 times negative 0.8 for A times 2 for C, all over 2 times A, which is negative 0.8. Okay, now we're going to go ahead again and type this into our calculators. The first time when we add, okay, our adding answer actually gives us a negative answer of negative 0.197. And we don't like that negative answer, right? We're going to cross it off. So then we're going to switch and we're going to change this to minus, and we're going to get our minus answer, which actually comes out positive, go figure, which is going to be about 12.70, let's say, seconds. So that's how long the ball stays in the air, again, on the moon. Now let's solve for Earth. Our Earth equation is negative 4.9 t squared plus 10t plus 2. And again, we are setting this equal to 0 because it will stay in the air till it hits the ground, and that's at a height of 0. So for this one, our A value is negative 4.9, our B value is 10, and our C value is 2. So we have negative and then 10 plus or minus the square root of 10 squared minus 4 times negative 4.9 times 2 all over 2 times negative 4.9. So a lot of similarities, but we changed our A value here. Again, we're going to get two different answers. When we plug all this in and we use our plus sign, our adding answer gives us negative 0.18. So again, we don't want negative time, so we're not going to keep that answer. When we change this to minus, which I did not want that to happen, keep switching me to eraser. Our subtracting answer is going to be about 2.22 seconds, which is a positive time which we will use. And so this is how long the ball was in the air on the Earth. So it's going back to the original question, how much longer will the ball stay in the air on the moon compared to the Earth? We just now have to subtract these two answers. Okay, we're going to take our 12.7 and we're going to subtract our 2.22, and we're going to get about 10.48 seconds longer that the ball stays in the air on the moon compared to the Earth. Okay, this was a good time. Try your homework problems. There's only 6. You can do it. Really use your notes and try to think about what it's asking you. Okay, you can do this.